Okay, so in this video, I'm going to go through parts of 3.4 and 3.5 that I haven't done. So the other parts of this problems, as well as 3.6 and 3.7, I've already done in my other videos, and solutions of the Dirac equation and the Hamiltonian, whichever ones, but I've done them before, so no reason to go through them again. But two things I haven't done are, well, I guess three things have proven these identities. So that's just what I'll do. Is that all of? Yeah, okay. So first thing, I want to prove that U bar contracted with V is 0. And similarly, V bar contracted with U is 0. So we have our spinners here. And yeah, I'll come back to the other ones. But so to do that, all I have to do is if I take U bar R of P dot with Vs of P, I just write out what that is. And it's yeah, almost immediately. So this came up again in the solutions of the Dirac equation. I prove a few identities, and this comes up. But this just ends up being equal to m. So this is minus m, this plus m times this. So this is 0. Then we have the next one is UR dagger of P contracted with Vs of minus P. So that we can do the same kind of way, or just write it out. So when we do Vs of minus P, it's only the spatial part of P that is flipped. So in this dot, I'll have, you know, the spatial part of this dot product is the same, but the time part is the same, but the spatial part flips. But that's the same as effectively, that's the difference between sigma and sigma bar, is that the space parts have different signs. So effectively, it just makes sigma equal to sigma bar and sigma bar equal to sigma. So yeah, so I've written that here. So they flipped. And then when I multiply it through, again, I get the same kind of thing. I get m, I'll get n minus my m, and that'll cancel, and so this is 0. And then finally I have these, and then I'm not doing, you know, obviously this works out the same way as this, and then the opposite, VR or dagger with U would work out in the same way as this. So then I have this outer product relation. So you can work that out. So I just write out the sum, and I have these outer products. And here I've got, you know, the S terms, and then I've just written this, meaning I get another term that looks the same, only with R instead of S. And I multiply this thing through, and then I do this outer product. So to do the outer product, you just, you know, the top left, it'll form a matrix. So the top left element is just this times this, bottom left is this times this, and so on. So I end up with this. And then I can, so this outer product of so these are my basis spinners. And the outer product of the basis spinners is basically, or the sum. So if I do the outer product of one basis vector, I will get basically half of the identity matrix, and then I'll be adding that to the other outer product of, you know, 0, 1, 0, 1. So when I do the sum, I'll end up getting a 2x2 identity. Hopefully that's clear to see. But basically, I'll get the same kind of thing, and then I'll have an epsilon s, epsilon dagger s plus eta, or epsilon r, epsilon dagger r, and that will give me a 2x2 identity, and then I just suppress that, and so I end up with this kind of thing. And this I think has come up before, this form of this matrix, which I can write like this. So again, this is just M times the 4x4 identity. And then using our gamma matrices, writing those in terms of sigma and sigma bar, it's clear that this is P cross.